There we go. Hello everybody and welcome to Handmade Hero, the show where we code a complete game live on stream. We did some work on lighting last weekend, and today is day 391, so if you're following along at home, you want to grab day 390's source code. If you take a look at where we left off, we actually were in a pretty good place in terms of just really basic kind of, the rudimentary lighting. Now if I go ahead and build here, there we go, and I run the game, it seems like CodeXL has kind of permanently destroyed our Visual Studio in some way. It's like now when we launch Visual Studio, it takes like eons for it to load, and we have no idea why. Just, who knows? Maybe that's just how Visual Studio is, because Visual Studio is amazing. But we had done the work for lighting the world from a single light source like this, and we played around with the specular effect of it. This is like got a tight specular highlight here, and right now the light position is locked to the hero's head just so we could move it around. It was just an experiment. And you can see we've got kind of a specular highlight here that travels around and bounces off shapes. As if it was a fairly mirrored shape, a little bit glossy, obviously, compared to a real mirror. But that's, basic Phong lighting, and it works mostly the way you would expect. Now, what we talked about last week at the end, though, was, of course, that, we have a lot of things that we might want to do now in order to make this lighting useful in the general game sense. So, two things kind of come to mind rather immediately, right? One is that we would potentially like to set these responses to the light per surface, right? So if you take a look at what, as we sort of travel around, you can see that this light behaves the same on all surfaces. So each one of these cubes, as well as the hero himself or any other sprite in the world, is all behaving with one particular reflection model. Even though we are only, in this case, we only did like a very simple Phong model, for example. And we'll probably talk a little bit more about lighting models in a bit, but even though we only did a very simple thing, which is just like a specular and a diffuse coefficient, if we wanted to make the world appear a little more varied in terms of its surfaces, we could already do that just by allowing the parameters on the Phong model to vary per surface, rather than having every surface need to use the exact same Phong parameters, right? So for example, if we wanted this cube to appear very diffuse and this one to appear very mirrored, all we would have to do is change the coefficients for the Phong model between the two of them, and you would immediately see a difference there. Right now, we can't do that because we have no way of varying the parameters per surface. We don't specify any kind of additional information with the surfaces that would allow the game in the renderer to know what kind of surface it was looking at, right? So that's one thing. Another thing is that we don't really have any idea at the moment how we would do like more of them, right? We just hard-coded a simple Phong reflection model into our shader. We don't have any idea how we would, do something more like 10 lights, 20 lights, 30 lights. We could make a for loop in the shader, right, that loops over the constant store, and the constant store has that many lights in it or something. So there are trivial extensions of it we could do, but is that really going to be an efficient way to do our lighting? Is that feasible, or is that going to be cost prohibitive, and so on? So that's another thing. And then finally, we also obviously have no indirect lighting. So we're only computing lighting from a particular light source where the light source shines off of something. There's also some ancillary things we can do. For example, now that we have lighting, you can see things like radial banding where the color fidelity isn't high enough. So dithering there would improve the visual quality of that, for example. So there are some other like cleanup kinds of things we can do, but that's like really a fairly minor thing compared to the other aspects of it, which are kind of more critical, right? You can ship a game with banding, but you can't ship a game with one light. I guess you could, but it'd be kind of questionable. So we kind of got to start to attack these, and obviously, you know, we don't want to spend an infinite amount of time working on the lighting because you could, right? Lighting algorithms are still an open area of study. You know, every new AAA game that comes out, or I should say engine for AAA games, that comes out, whether it's, you know, Unity or Unreal, or if it's one of the more custom ones like Frostbite, or Snowflake or Snowdrop or whatever that one is from Ubisoft, blah, blah, blah. They all have ways of doing lighting that vary dramatically, right? Like everybody comes up with new ways to do it. In fact, even like the idTech engine, the new one for Doom, did a totally like, you know, new take. I mean, it was not totally new take. It was like a sort of a extension of the checkered, like gridded voxelized rendering that you break up the scene into sort of like small pieces and render them separately so that you can break down what lights contribute where and stuff like this. So you know, every time a new engine comes out or there's a new upgrade to the engine, lighting is something that's typically improved or at the very least changed, to attempt to find like sort of the holy grail of like it just magically works. So you put lights in the scene and they light the scene the way lights light scenes. You know, none of them is perfect and none of them quite works right. They all have drawbacks or weirdnesses or things, but they keep getting better. And so there's kind of just an infinite sinkhole there at the moment that you could go down in terms of how, you know, what you want to do to try to make the best possible lighting for any game, regardless. And we're not going to try and do that. But we are going to see, you know, what could we do that's something reasonable here that would improve some of the aspects of our lighting. So, for example, one of the things that I think would be probably useful for us to explore is rather than getting our lighting from something like a single vector in the constant store of the shader that just says this is the location of the light, what we would rather do is have some sort of a way of producing lighting information in the same way that we produce our actual, like the actual game information for view. And that is to say that we have a pipeline now that we can use to render things, right? We have a pipeline we can use to render the game world, and we are rendering the game world. It would be probably advisable to do something in that system that allows us to render the lighting of the world. And what I mean by render the lighting is produce some kind of intermediate lookup structure that allows us to query what the lighting should be at various places in the world without having to recompute the lighting in its entirety. So for example, one very common way of doing lighting these days is a method called light probes. And let me sort of give a brief sort of idea of what a light probe system looks like. And then you can hopefully see more what I mean about creating an intermediate structure. So here we go. Just want to make sure my Milton is working, and it is. Here we are on day 391. So let's talk about light rendering. So one of the things that we haven't talked about yet, right, is we sort of talked about the basics of lighting, and we gave this sort of, discussion about like, all right, so we have these surfaces, and the surface has a particular normal, and there's all this sort of light that's incoming to the surface, right? All of this light is incident light on the surface, and that light is collected if the surface is not transmittive. So, you can have surfaces where light comes from the back, like a rice paper screen or glass, and light from the back comes through, right? But if we're talking strictly about reflective surfaces, at least for the moment, we're talking about a hemisphere here of light that comes in. So there's, if you looked at it in 3 dimensions instead of 2 dimensions, there's a hemisphere of light here where every direction conceivable on the front side of this surface, light is coming into it. And similarly, there's an entire hemisphere of light that's bouncing out of it, right? And fortunately for us, all we really care about for the individual pixel that we're rendering, not the world, because the world, when we care about how the light bounces around in its entirety. But all we really care about is that one light bounce that goes out towards the camera from that particular location on the screen, right? So what we want to know, typically speaking, is for all the incident light across the entire hemisphere, right, what actually bounces out in the direction of the eye. Now, obviously, you can get extremely complicated versions of this, and if you're talking about a more backward scheme like a ray tracer, where we start here and we come out, we hit this point, and we go, oh, let's collect samples by shooting out from the hemisphere into various places and see what we get, it's a little more easy to understand how you might take a reflectance function, so some idea of how the surface is supposed to behave, where does light bounce from and to in some kind of coherent way. It's a little more easy to understand how you might implement that because you're literally doing the operation of the reflectance function just in reverse. You're going, oh, I come out to the surface, I hit a particular point, I can then go out and sample the light in various directions, and I could pick which directions I sample based on how I know that surface reflects light. If it reflects a lot of light from over here in that direction, but not much from over here, I can take a lot of samples in that direction, right? And furthermore, for every sample I take, I know how it should be weighted, because I know what the reflection coefficient is for that bounce, right? Because I usually have something called a BRDF or something, or BRS, I think they're BSSDF. There's all kinds of names for this, but bidirectional reflections distribution function, I believe, is this one. Bidirectional subsurface distribution function is this one, which allows bouncing in here and stuff like this. I don't know. This might be BRSSDF. I don't even know. It doesn't matter. The point is, there's a bunch of 4-dimensional functions. And people even take real surfaces, like they'll take these real surfaces and they'll put them in a thing called a gonioreflectometer or other kind of like ridiculous machine designed to measure their reflectance. And they actually come up with transfer functions that say for each individual incoming light direction sampled at some discretization, here is what the outbound light in one other direction is. So it's really the 4-dimensional function. You can act as transference right. So you can actually simulate real surfaces this way by saying, here's the actual way that this surface reflects light, and I will actually simulate it in my renderer by going, what's the incoming angle, what's the outgoing angle, use the coefficient of transfer that we actually measured from the real world, right? So that's like, the sort of ridiculous high-end, we've got a render node cluster rendering these things, and we don't care how long it takes. We just want to produce a really accurate image, right? Well, you can do that. But the question becomes, I want to now do this in a game, and I want to do, I want surface properties in a game, and, if you're somebody, again, like, let's say you are the team working on something like, Frostbite or Unreal, one of the higher end rendering engines, what you're trying to do is basically this. You still want to have these surface parameters that give you something like a BRDF that's actually been sampled, but maybe it's not quite as detailed as that. It's more approximate, like you bake it down to some reasonable number of parameters that kind of just shape the reflectance function so it can be fit to real data, or approximate the kinds of real surfaces that you commonly have in games. And you you can come up with some reflectance functions that make sense here. But the question is, well, what do you do in the rendering context? Because you don't necessarily have the ability to shoot rays around anymore. That's not a thing that the graphics card necessarily is going to do. And then there are some systems that even try to do that, right? Like voxel cone tracing renderers, for example, do this. So it's not, ray tracing is actually not done these days because GPUs are so nuts. You might actually do something that allows you to do that. You don't tend to do it the same way that a strict ray tracer does. Those tend to use things more like KD trees for acceleration and stuff like this. In this case, you're talking about something that needs to be handled in a forward process. So you're talking about something that usually works more with voxels, something that the GPU itself can produce for acceleration structures in terms of lookup. But all that being said, despite those facts, the rendering process still might do some ray tracing in there. We're not going to really consider that because that's going a little bit too banana cakes, like I said, down that rat hole. You can go down it, and people do, but we're not going to go that nuts. So we're talking about a more traditional version of the renderer here where we just want to do some kind of forward rendering, but we want to be able to have our surfaces perhaps do something a little more interesting here. So what we already did is something that kind of looks like a Phong reflectance model. And what a Phong reflectance model does is a Phong reflectance model assumes a couple of very drastic, I would say, and rightfully so for the era in which Phong was created, because remember, we're talking decades ago when computing power was even offline rendering was very limited, and you couldn't go nuts with things. Phong makes a very important simplification that's very drastic. And that simplification specifically is that while it does not really simplify the concept of the eye much, we're still talking about a point eye source a lot of the times. Sometimes you get a little more complicated where you have a lens aperture, but the eye is usually not the hard part unless you start talking about four-dimensional like motion blur kinds of things, stuff like that. So assuming the eye, we're just talking about a stationary eye. A point approximation for an eye doesn't lose you that much, especially not with surface reflectance. And so when we take a look at the eye here and we're talking about this approximation, yeah, we're approximating some things. So first of all, we're not taking into account the fact that the eye is really a lens that focuses a cone to a point. And we're not talking about the fact that that focusing process actually has depth of field to it and stuff like that. So we lose some effects at the eye, but in terms of surface reflectance, we don't lose a huge amount other than that cone. But what Phong does in terms of an approximation that's so much more drastic than probably what we would want is it assumes that the light is a point, right? And I'm not talking about just the light, meaning a light in the world. I'm talking about it assumes all lighting incident on the surface comes from a point light source. And even if you want to extend it to multiple points, like multiple lights, you're talking about multiple single points of light. And the reason that this is such a drastic simplification of the lighting model is just because most surfaces get their look from the fact that light comes from a tremendous array of sources around it. Most surfaces are going to get at least 50% of the light that you see coming off of them from indirect light. Because, light sources tend to be very small and they tend to be very few. Whereas that light, even though the light source is very small, bounces all around something like a room, for example. And, it will mean that any individual surface that's trying to, that you're looking at is going to be getting light from so many more places than just the actual light source itself. Never mind the fact that you've shrunk that light source from an actual shape to a point. The real simplification here is that you're not collecting light from everywhere else, right? And this goes double for outdoors. Even though the sun is the closest thing to a point light source you're probably ever going to get, it's very small from our perspective, right? Like, yes, the sun may be huge, but from where we can see it, it's really tiny. And it's so far away as to be highly correlated. So, like, its light is almost directional, right? So it's kind of easy to abstract the sun's light source. However, the atmospheric scattering being what it is in the Earth, the light actually during the day comes from a huge canopy of blue, sort of whitish blue sky dome, right? It's a big hemisphere of blue that's lighting up the world. And so, again, there really is no circumstance that you ever really look at. You'd have to construct a really strange sort of flashlight holding kind of a thing to really get anything even close to what a Phong lighting model is going to give you, specifically because it just doesn't take into account the sort of broad reception of light that you can get from the way the real world does its lighting. So that's the really huge simplification that you get with a Phong lighting model. And the problem that we would have in Handmade Hero is if we want to move past that, we would need some kind of way to take the hemisphere of light that's being ignored by the Phong model and say, if we want to step up to something better, the problem here is not the Phong model per se, it's that simplification of the Phong model, and that simplification of the Phong model is what gives us the ability to compute it with just all the information being where the light is. I mean, we have no other information than just where is the light. So if we wanted to step up from that, we now need information about what the whole hemisphere of light is. Right? What's all the light coming in across the whole hemisphere? And once we had that information, we could even just use something like a Phong lighting model and take lots of samples and produce perhaps a better result. So the actual concept of a diffuse specular coefficient or something like that with a Phong lighting model, that's not so bad necessarily. What the thing that makes it look really unnatural and weird is less that, although that is important to have more robust ways of shaping the reflectance, certainly. What's more important is the fact that we're just not taking into account how the light flows around the scene at all, and all that hemisphere of input. So one thing we can do in terms of storing and looking up that information, there are some interesting ways we can do that. The hard part's going to be figuring out how to produce those in the first place for a game that is generated on the fly, right? But let's talk about that for a second. So what would we do if we wanted to improve this lighting model by, ignore the lighting model itself for a second, but just say, we know we're going to move away from something that treats lights as idealized point sources, and we want to move towards something that has more sort of global information about the irradiance of light at a particular point in the world that we're trying to simulate the lighting. And the answer there is that, there are some simple techniques you can use. I mentioned light probing, and that's probably the easiest one, and it's really easy to describe. What that means is, well, let's assume temporarily, and again, this is the hard part of the problem for something like light probing, so it's not an easy thing to assume, but we'll talk about that in a second. Let's assume temporarily that you could do something to calculate the lighting, but it was pretty expensive, and you certainly weren't going to do it per pixel. What would you do if you could afford to, say, do that 20 or 30 times, but you can't afford to do it 1920 times 1080 times, right? So you can do a few determinations of what the lighting might be in a few places, but then you can't do it everywhere, right? So what would you do? Well, light probes are one way that people have attacked this problem. And they're pretty straightforward. They rely on what I always say is the most important equation in all of computer games. Linear interpolation. And how they work is they say, okay, suppose I'm looking down at the game world here. Here's my hero. And I know the hero is going to move around the screen. And I need to be able to light the hero no matter where they go. And I also need to light everybody else. So, we've got the little snake dude who's coming in here or whatever. And everybody needs to get lit. How am I going to do it? Well, let's say we have enough horsepower to compute what the lighting hemisphere and that sort of stuff would be at, let's say 12 places, right? Well, what I can do is I can scatter those 12 places in a grid. Like so, right? And if I scattered these places around and I compute what that lighting is going to be at each individual place, what I can do is I can produce some intermediate structure for storing it. And in this case, because GPUs tend to have this built in, they usually use a thing called a cube map. Now, you can use other sorts of things, like there's various ways of storing like spherical, harmonic style, reduced coordinate versions of lighting. There's all sorts of other things you might do. But one thing that's very common is to store what's called a cube map. A cube map is literally a cube with a texture map on each of its faces. So it's just a glorified way of saying I have 6 square textures. And the only thing that makes it a cube map per se, rather than just making 6 square textures, is that it's fast to do lookups into it based on a normal. So basically, the computer graphics hardware, before it was more programmable, nowadays you could write your own cube map lookup function, so it's really not a big deal. But in the old days, it was a big deal, because they basically put in special purpose hardware just to do this. And it was to say that if I have a normal that's pointing in a particular direction, I can figure out what pixel I hit, or texel I should say, on the cube map. So it will look at which direction the normal was pointing, whichever face that would have hit if you started in the center of the cube and went out. It picks that face, and then it picks the pixel that it would have, or texel it would have hit. I should say 4 texel, because it will still do a bilinear sample if you want it to, right? So it can smoothly do it. But that's a cube map, very simple concept. It's basically just 6 textures you can look up in a special way. And the interesting thing about this cube map is that this cube map is a good way to store the inbound lighting at a point, right? Because if I take a particular point and I rendered the world, let's say I literally just used my same graphics pipeline to render the world in each of 6 directions, I would get an image that told me the inbound light at that point, right? And then I can use these cube maps to light something. So if somebody's right here, I can do a bilinear sample between my cube maps, right? I would simply say, what is each of these cube maps say the lighting is in a particular direction, if I want to know. And then I just bilinearly filter that based on where I am relative to the cube maps, and now I've got interpolated lighting. It's not perfect, but it's useful, right? It can give you approximate lighting when you can afford to compute the lighting in certain places, but not everywhere, right? And furthermore, if you want to, depending on your circumstances, if you have additional knowledge, you can leverage that additional knowledge, meaning that if you happen to know places where the lighting changes a lot, you could put more cube maps down in that area. I could more densely put them here, for example, if this were an area where the lighting was very finicky, and I could leave them sparser over here where the lighting is maybe not so variable. Maybe there's no light sources over here, for example. Maybe all the lights are over here, and so the lighting changes a lot in this area, but over here it's just kind of smoothly decaying, so you don't really need to know much about it, right? So that's, one example. And you can see why that's kind of useful, because basically what it does is, even though that can be kind of expensive, so obviously producing all these cube maps would be expensive, it is a way of reducing the cost down to a fixed number, right? So you can just say, how many cube maps can I afford to make? If that number is 16, well, I put 16 down. And now my performance is consistent because it's only 16 times cube mapping, whatever that amount of rendering cube maps is. And then I know I always have a constant time per pixel from then on. No matter how complicated the lighting is, it's never going to produce more complicated per pixel lighting, right? So that's a pretty interesting way to kind of look at lighting in the world, certainly. And it's a pretty simple caching mechanism, right? It's a way of sort of caching what the light's doing in various areas and then reusing that to sort of upsample it so that it's as if you kind of had it in all the places, but you don't have to actually compute it in all the places. Will it be accurate? No. Will it be good enough? Probably. Now, the interesting thing about this, though, is that it doesn't solve the problem completely. It's just a step in solving the problem. It's a way to cache intermediate lighting information that be useful. It might be useful for us in Handmade Hero. It's useful to be aware of these kind of schemes, certainly. And why does it only solve part of the problem? Well, part of the problem that we have here on Handmade Hero is we don't have a pre-pass. So a lot of times where you'll see light probing being used, it does solve the problem completely, right? If you have a game that has cube maps in it, it might be that solves the problem completely. Why does that solve the problem completely? Well, because you have an offline step. So what will often happen in a more simple renderer, for example, is that the level designers create levels. Those levels are baked offline, and some scheme that actually does accurate lighting computation produces cube maps for these light probes. So for example, you will go, okay, done with the level, bake the lighting. It'll go around dropping cube maps down. It will do a ray traced render to calculate what the lighting is at each texel in the cube map using some kind of a ray tracing scheme. And then when you go to run the game, you have all the information you need. You just got these cube maps that tell you what the lighting is. And the only problem is you can't really do dynamic lighting with that, so you have to compensate by adding the dynamic lighting in somehow. But since those are usually minor for these types of games, which usually don't have that many moving light sources, or if they do, they're like explosions or things that don't have to be super accurate, they're just temporary. That solves the problem, right? Because the offline version can just use whatever slow, random ray tracing thing you want, and the online version just has the cube maps that it needs. And that's all good. The problem with our situation is we don't have any ability to do offline lighting. So we still have the problem of how to produce the lighting in the first place, and this is a real problem. It's a real problem because we don't know what the lighting of the scene is until we create the lighting of the scene. This is the eternal problem of ray tracing. It sounds like a circular statement, but it is a circular problem. The statement is accurate. What do I mean by that? Well, okay, let's think about this for a second. I've got two surfaces. They're in the world. Here's surface A, and here is surface B, right? And I just said what I want to do is I want to create a hemisphere of incident light so that I can light this surface properly. And hey, guess what? I also want that over here, right? I want a hemisphere of incident light so I can figure out what the lighting of this surface is in any particular direction. Well, I start by saying, okay, I'm going to create that for surface A. I need to create a hemisphere of incident light. Let's see what the incident light is in this direction. Well, hey, guess what? In that direction, the light comes from light reflected off of surface B. Okay, what's the color of surface B? What color light and how bright does it reflect in that direction? That's the information I needed to know, right? Well, in order to do that, I've got to produce a hemisphere of light. Let's produce a hemisphere of light. Well, in order to produce a hemisphere of light, I need to know what light came in from this direction. What light comes in that direction? Well, it's whatever A reflected in that direction. Okay, let's compute what A reflected in that direction. In order to do that, I have to produce a hemisphere of light. in order to produce a hemisphere of light, I have to know what light is incident on A, for example, in this direction. And it's B, and A, and B, and A, and B, and A, and it wouldn't even ever terminate, right? So one of the classic problems of light transport is, very specifically, that because the real-world activity of light is a bunch of photons that bounce around the room ad infinitum till they hit something, like an eye or a camera, or get absorbed by a surface, it's incredibly difficult to produce the initial lighting for a scene because it's a very dynamic, highly diffusive process that really defies any kind of exhausted computation. You cannot simulate the lighting for a scene in reality. Photon tracing just doesn't work. There's been schemes that do it, but it's way too expensive, the number of photons you have to shoot. So any photon scheme that has ever really done anything useful massively approximates the photons in a lot of ways, right? So what we need is some way of producing a very approximated solution that is still related to the actual solution that involves this sort of infinite bouncing of things around. And infinite's the wrong word. It's not really infinite because obviously photons don't bounce around forever. Eventually they get absorbed somewhere. But if you ever have held two mirrors up next to each other and seen the sort of what appears to be an infinite copy of images, well, that's how many times those photons were bouncing back and forth, right? So while it's not infinite in the real sense of the word infinite, it's certainly infinite related to today's computing power, because when you think about how many billions of photons there are, or trillions of photons there are bouncing around a scene, and the fact that some of them may bounce hundreds, thousands, I don't know, millions of times before they're absorbed. I don't know what the average life of a photon is in that sense from a light source, but it's a lot. It's a completely intractable problem in terms of the computing resources we have. So what we're typically trying to figure out is, what are approximate algorithms we can use that tend to get similar results as what would happen if you bounced all the photons around like that, but that absolutely in no way involve bouncing those photons around like that. And so the typical way that these are solved offline is always what are called Monte Carlo schemes. And Monte Carlo schemes, it's called Monte Carlo integration, and really, obviously, Monte Carlo refers to sort of the gambling aspect of it. But really, all that it means is they're randomized integration schemes. What randomized integration schemes are is they're saying, well, okay, so I've got some function that I know is simply impossible for me to actually compute, right? So for example, in this case, we're talking about integration. We have an integral, right, over a hemisphere. And we know that there's no closed form way to produce that integral. We can't even sample the integral densely enough. Forget it, because at every function that goes out from the hemisphere itself bounces around on hemispheres. So the dimensionality of this function is just huge. Forget it, right? There's no way we can even consider solving it directly, so don't try. And what these schemes, the reason that they're called Monte Carlo integration schemes is because what they do is say, well, okay, if we have something that's too high dimensional for us to really solve, we can still take randomized samples and combine them in ways that produce an approximate result. And that's what pretty much all high-end ray tracers these days are. They are all Monte Carlo integration schemes, and they range from incredibly stupid, such as pure Monte Carlo, like pure random selection of rays with only a slight the only real modification being looking at the lighting equation for the surface and biasing in directions where the lighting contribution is going to be the highest, right? That's about it. So those are like kind of more pure Monte Carlo, pure random, I should say, integration schemes. All the way to ones that are actually incredibly sophisticated and complicated to understand, such as Metropolis light transport or Metropolis manifold tracing, things like this, that involve very complicated analysis of how paths behave and how we can assign probabilities and properly combine probabilities along those paths to produce the highest accuracy integrals that we can and know that we'll always converge to a fair solution no matter how many samples we take and blah, 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 right? So there's a wide range of these schemes, but they all boil down to basically the same concept, which is that we know we can't actually sample the function densely enough to produce an answer. So instead what we're going to do is randomly sample it, and we'll just try to come up with schemes that put those random samples to the best use possible. But that's all we're doing, right? So that tends to be how these things are worked out. And so the answer to the question of how do you solve a problem where the light bounces around infinitely, the answer is you just kind of use a termination criteria. What will typically happen in this situation, for example, is what you'll say is, all right, let's pick, because of the Monte Carlo nature, let's pick a number of bounces ahead of time out of a hat, sort of, if you will, right? So we'll say that this is going to be a 7 bounce path, right? We picked 7 out of a hat, random number. Why did we pick it out of a hat? Well, if we didn't pick it out of a hat, we would be biasing ourselves towards a particular number of bounces, which will affect the lighting solution. So if we want to try and produce a fair lighting solution, we need to pick everything randomly, right? And this is an interesting aspect of Monte Carlo integration that I'm not really qualified even to give you a good explanation of it. I don't study probabilistic light transport, and it's a very touchy field. So it's easy to think you wrote an unbiased Monte Carlo integration renderer, and you didn't. So I will leave that kind of explanation for the experts. I'll simply say that you need to study this stuff a little more carefully and make sure that when you are producing a ray tracer of this nature, you have to really understand where you might introduce bias into the system. Bias, of course, will then produce, brighter or darker images in places and things like this because you have bias towards a particular type of solution that is not really fairly sampling the high-dimensional integral in a truly random way, because a truly random way of sampling it, of course, will not bias it. It will produce, on average, the correct result. This is why we talk about, you'll often see, is this an unbiased or biased, right, renderer? And these are terms used more or less exclusively in the offline, or some of them are kind of sort of offline, like Brigade from Octane, for example, is a real-time-ish ray tracer sorry, not from, what are they called? They're called OTOY, O-T-O-Y, I think. Octane is a real-time ray tracer, for example, that tries to be, I think, largely unbiased. I don't know if it actually succeeds, but I think it does. But anyway, so these things are used largely because in the offline world, you actually care about converging reasonably after some number of samples to a solution that correctly approximates the light on average. A biased renderer will not necessarily do that. An unbiased renderer will. The way to look at this probably, and this is kind of getting a little off topic here, certainly, but if you imagine, I'll give you a case. Here's 2 graphs. Suppose that this is the brightness that a particular pixel should be in either case. So this brightness is some number of lumens, right? Some color value, whatever it is. If I am an unbiased renderer, then as I take samples to produce my solution for a particular pixel, my lighting value looks like this, right? My lighting value sort of converges on the correct sample on average. So as I take samples, they're going to be, and I guess that's probably the wrong way to do it. Right? So as I go through this, I'm going to kind of narrow in. I'm going to start off kind of wrong, and then as I take more samples, I'm going to converge on average towards the correct solution, right? On the other hand, a biased renderer usually looks more like this, right? Eventually, it will get to the correct answer, but it starts off in the wrong direction and is never going to be on the other side of the wrong. It's never going to be wrong in the other way. So it tends to be wrong, like strictly undervaluing or strictly overvaluing the lighting contribution at a pixel. And then the more samples you take, it may eventually converge to the right result, but it will always approach from one side. Now you may ask why you would care about this. The reason you would care about this is because if you look at an unbiased rendered image, because you know that you're taking random samples and you're going to go like this, or rather that your random samplers are truly distributed around the lighting of the point, what you're going to see on the screen is a true representation at all times of the lighting. It's just going to be very noisy. And as you take more samples, the noise will go away. So you'll start with an image that looks like the correct image but is very noisy, and then it will get less and less noisy. Why? Because any two neighboring pixels, while they will both be quite wrong at the beginning, they will be quite wrong in opposite directions potentially, right? And not only in opposite directions, but different magnitudes, right? Because you're all over the place. On the other hand, a biased version will just be like a really overbright image. The whole image will be overbright, or the whole image will be dark, and then it will get brighter as it goes, right? So at no time until the final convergence will you ever really see an accurate version of the image. The reason this is kind of nice is because A, you can stop at any time and have an image that looks sort of right. It's just much more noisy than it should be. And B, it helps pretty well with previewing, because even the first thing that comes up on the screen after very little computation time with an unbiased renderer is at least sort of representative of the overall image lighting, right? Whereas this one may be nothing like it. You may start the render and it appears like you can't see hardly anything at all and it's way too dark and you're like, oh, I should crank up the light values. But in reality, if you'd let it run to completion after 7 hours, it would have been quite bright and fine. That's not something that will happen with an unbiased renderer, right? All right. So again, sorry to get too far off topic there. I just wanted to, I always try to like touch on various subjects when we talk about these things so that people who are interested in various aspects of this know that the stuff's out there that they can go read about or find out about if it's something that sounds interesting to them. Okay, so given that we've got this situation, let me go back to what I was really trying to explain, which is how do you break this problem? Like how this seems kind of like a relatively intractable problem. How are we ever going to fix this infinite bounce nastiness of not knowing what to do? Well, Monte Carlo solves this rather nicely by saying we'll just pick a number of bounces ahead of time. Who knows what it is? It's just any number of bounces, does not matter. And then what we're going to do, here's my surfaces in the world, here's my camera or whatever, is we're just going to do it, right? We're just going to say, all right, send it out. That's a really bad light. Right, there we go. Send it out, right? Bounce it around. What did I pick? 7, right? So it's 7. 1, 2, 3, 4, 5, 6, right? There's my light path. And now I'm here. And I know that this is supposed to be a 7 bounce path. So what do I do now? I go, where is an actual emitter, right? Where's a light source? And now trace to the light source. And now I have picked on that 7th bounce, I've connected it up. I've connected the eye with the light and can compute a lighting contribution for this path, right? So that's the way you break it, is yes, these things can bounce around forever, but if we pre-pick ahead of time basically a kill number, where we basically say, after this number of bounces, we will specifically target the light source and see what's there. That's the way that you break that cycle. Now again, doing that in an unbiased way can be very difficult, because the fact that you're picking intentionally something that hits the light source at some point can be rough. But again, that's sort of a separate topic of study. Similarly, another thing you can do is at every bounce, you can check the light source. So I could say, every time I hit a surface, let me see what the light source would contribute to the surface, right? We'll add that in, then I'll do the bounce, and then I'll do the light, right? And I'll keep doing that for every bounce. I'll figure out what the light contribution is for the partial path as well, right? And so in this way, you just build up a collection of light path contributions throughout the scene, and that gives you an approximation to what the light is actually doing that is good enough for full lighting. Now, if you want to see these in action, again, it's because we're not writing one of these, because we can't actually really write one, because we need something that runs in real time on reasonable hardware. But you can take a look at, say, Maxwell render and Octane render. Here are some sort of more state-of-the-art offline renderers, and you can take a look at what they look like. I don't know if there's a good... you can kind of see the kinds of images they produce here, obviously. I don't know if we've got here. Well, here's a demo. Oh wait, no. So yeah, you can actually try these, I guess, right? I don't even know what this is going to do. This is probably going to crash my machine. I don't really want to do that. I would rather just see a video here. Let's see if Octane Render has a YouTube video. Let's see here. Go ahead and just mute the sound here. So here's somebody running Octane Render on a machine that's really beefy, right? But you can see that, it's pretty fast, right? Here's him pushing whoever this person is, I don't know who they are, pressing the render button. Yeah, you can see them kind of drag the scene around, right? And you can see that, with that kind of GPU power, it computes the lighting pretty quickly. And you can also see, like I was saying, how it kind of it starts off pretty noisy and then converges a little bit. I don't know if this is an unbiased renderer. It looks to me like it starts off a little dark, honestly, so it might be more of a biased renderer, I'm not sure. But you can kind of see how an offline renderer works. And with that much GPU power, you can also see that it's not real time, but it's close. It's like maybe 1/10 real time or something to produce an image, right? And so that's pretty good. Maxwell render is less of a real time in that sense. It's more about accuracy. And I don't know if we've got a Maxwell render video. I don't know if we've got one here. Let's see, Maxwell render 4.1. Let me see if there's a video of that happening. Let's see. I don't know. I don't know if there's anything particularly good here for Maxwell. Oops. I said videos. Do I have a YouTube? Maybe? Maxwell render 4.1. All right, let's take a look here. All right, or we could just watch an ad for something instead. Okay, here we go. Yeah, so you can see here, this is... they've got sort of a preview window thing going here. I don't know if we've got any good shots of them actually rendering. Yeah, I don't know. Well, point being, you can go find these yourself, and most of them have demo versions as well, so you could probably download them and play with them. But I don't want to waste any more time looking for good videos of them. Point being, there are plenty of renderers out there that are this way. There's also some free ones. I don't think Indigo is free anymore. Indigo used to be one that was free. And there's one that's kind of crappy called Cycles that's built into Blender, for example. That one's obviously also free. It's real bad, but it's free. But you could, take a look at one of those as well. So there's a lot of stuff out there that you can look at if you're more interested in learning about this sort of light propagation stuff. And you can read papers on it. There's hundreds of papers every year written on this topic because light transport is just a tough problem. And it gets easier every year as they give us more and more CPU and GPU power to play with, thanks to hardware adding more and more cores. Light transport is a very parallelizable problem, so it succumbs very nicely to huge amounts of flops, which is why GPUs have been such a big boon for it. And you can get things like that Octane render where you're kind of almost real-time light transporting around fairly complicated light transport. Certainly awesome. But all that being said, that is the offline version. And unfortunately, unless you are doing if you're working on your own product at home, that might be very relevant to you because you might be able to just do a little offline Monte Carlo ray tracer that can produce a totally reasonable set of light probes for your game, and then you're done, right? And incidentally, I believe that's pretty much how the Witness worked. I didn't do the renderer for the Witness. That was Ignacio Castano did it. So I don't really know very much about how it works, but I believe it was a light probe based renderer. And the way that it did that was it produced light maps for surfaces and light probes using an offline ray tracing process. I don't know that it was exactly ray tracing. I think it used GPU acceleration to actually just render successive versions of the scene or something. So I'm not really sure exactly how it did it. Because again, I didn't write that part of it. But it was offline. So it basically produced light probes and surface lighting offline using basically a light map baking machine, a light probe generating machine. And then during gameplay, it would sample from those offline produced results to give you the final render. And plenty of things work this way, right? So that's a very common technique, but it's not really going to work on Handmade Hero because we don't have a pre-pass. I wish we did, but we don't. And so we have to come up with some way of producing some lighting without the advantage of being able to spend a lot of time producing that lighting in an offline scenario. So we have to do something that propagates light around our scene online. And whether or not we use something like cube maps to store the result, we need some way of producing something reasonable, right? So what we need is something that takes n light sources, bounces them around to some degree, and produces approximate irradiance at places, right? That's what we're looking for. We want to be able to throw some light sources into this. Bonus points if those light sources can be creative, like Sky Dome, right? But if they can't, oh well. Point light sources, you can always just, as long as you can handle a reasonable number of them, you can always approximate most lighting by just throwing in more points. We need to throw in some light sources. We need them to sort of diffuse themselves. And then we need to be able to produce some kind of approximate idea about how the lighting is working at any particular point, right? And I don't have any kind of like preconceived idea about how this should work in a game like Handmade Hero. The sort of bounce is the hard part. I think taking in a bunch of light sources and just rendering from the light sources isn't particularly tough, right? It's not particularly tough primarily because if we just rendered cube maps directly, like every frame or every few frames, like update our cube maps sort of gradually or something if we had to. Even if you had like 1,000 lights in there, I mean, how hard would it really be, right? Rendering 1,000 light splats into a cube map is trivial. I mean, that's 1,000 little. You don't even need texture samples to render a light source because a light source is just a little point, right? So something where we're just rendering a bunch of lights into a cube map is pretty easy, I think. And so producing that element of it shouldn't be too hard. The hard part is the bounces. And the bounces are problematic primarily because they involve this sort of traversal of the scene, right? And if there's one thing that a GPU is awful at, it's traversing a scene. Why is it awful at it? Because we would have to send the scene down to it in the first place, which we don't really want to have to do, right? We have to send the scene down to it, and it has to do a bunch of intersections and searches through, which is exactly what it doesn't want to do. Like GPUs hate traversing memory randomly. They like having everything run in a very methodical, consistent way. I'm always sampling from nearby stuff and whatever, right? So GPUs actually hate ray tracing. It's like their least favorite thing, typically. So the bounce is a problem. Now, one thing that's interesting, and I'll point this out, is that in general, it's usually possible to turn, to transform, if you will, a area lighting problem into a point lighting problem just by using more points, right? And what do I mean by that? Well, let's suppose that we take a very, very simple scenario. I want to know, I've got a cube or something that's floating above a giant plane. And up in the sky, there is going to be a sun of some kind shining down, right? And I know that I can compute the lighting from the sun very accurately, very easily, because again, it's sort of a point light source. It's sort of easy to deal with. We already did the Phong version there. You can imagine us doing sort of more creative things with it. It's not very complicated when you're just talking about one point of light. And so the question is, well, what if I wanted to extend this scenario to include the backscatter from this plane? So this sun is also shining all on the plane. Maybe this plane, so the sun, let's say, is yellow. The plane, let's say, is green. And so we would expect to see some green underlighting on this cube. So down here, it should be kind of green. The underside surface should be almost completely green because the only thing can hit it is the bounce light of the green. So we want to see a yellow top, green bottom, right? Something like this. Well, one thing that we can do is say, all right, before we start, let's shoot a few rays. Not too many, maybe 10, right? Maybe 50. Not very many. Shoot some rays out from the light source and see what they hit. Wherever they hit, we will add a new pretend temporary light source with the color of whatever the reflected light is from that surface. So it's basically just produces a bunch of point light sources from a single point light source. We then light the scene with 50 point light sources and we're done. These will all be green, so this will see a bunch of green light sources. This will see the yellow light source, and that's the end of it, right? So there is a way to sort of turn a complicated lighting problem that appears to involve more than just point lighting into something that only involves point lighting. And so, that to me sounds kind of enticing. Because what I could do, for example, is every frame on the CPU, I could do some ray tracing to spread out my lights to various parts of the scene in a sort of homogeneous way. And then I could treat each of those as a point that I then render into my cube maps. And as long as I keep that number, like I said, to something sane like 1,000, rendering even 30 or 40 cube maps of a low resolution when the only thing I'm rendering into those cube maps are some points seems pretty doable, right? Now there's a little bit more to it than that, and so it's not quite as rosy a picture as I painted, and the reason that it's not quite as rosy of a picture is because in order to make the lighting work in a way that implies shadowing, which we would like, and we don't have to. Again, we're not trying to be a Pixar movie here. We're not trying to light the scene in a 50-hour offline render. Well, they don't allow 50-hour offline renders, I don't think, at Pixar, but a 12-hour offline render. We don't want to try to compete with that, but we do want to capture as many lighting elements as we can, and one of the useful ones is occlusion of the light sources. So for example, if I have, in this same scenario, let's suppose that I did something slightly more complicated, but again, still not particularly unusual, so you can easily imagine the scenario in which it exists. Suppose I have something that's just a simple fin here, and then I'm talking about the lighting on the cube with the sun. So all I've done is I've split my plane in half. And now what I'm going to say is this side is red, this side is green, right? And this is yellow, right? And I really don't need the fin, in fact. I probably overcomplicated it here to a large extent. Let's just say it's just two things, a red and a green. Well, now I would expect this underside of the cube to be more red, this side of the underside to be more green, in the middle it should be more of a wash, right? Because, especially this side of it is really only seeing the green, it can't see the red at all, so this should be more green, and the same is true over here. This one should have some red contribution, the bottom should have some contribution from both, right? So in that scenario, right, you can see why it's important to do some basic occlusion. Now, one kind of occlusion is just the hemisphere occlusion. So for this scenario, it's sufficient to simply say, well, only sample from the hemisphere. That would get me the occlusion that I want, right? But now if I go and I add the thing that I was talking about, let's say I put in a blocking plate here, right? And this is black. It doesn't reflect light at all, right? Well, that's a bad example because the light's coming from this direction. Okay, I can't quite do that. Here's the blocking plate here, right? So now this blocking plate doesn't intercept the light at all. The light still falls everywhere it would have because this blocking plate is just under the cube. Well, now the underside of the cube should get much darker, right? And the closer I move the blocking plate to the cube, it should get extremely dark because it can't see hardly any of the light. But if all I was doing was rendering these point light sources into the cube maps, or just even forget cube maps, no matter what I'm doing, if I'm only considering the point light sources and I don't see whether the point light source has occluding geometry in between it, I won't pick up that shadowing effect, right? So in that scenario, I've got a really nasty problem, which is that while it would be very efficient to do something like produce cube maps strictly from point light sources, what do I do about the fact that my surfaces will intercede? Now, the interesting thing about this is it may still be for a game like Handmade Hero that it's actually okay if you actually just wanted to produce the lighting by rendering all the surfaces and all the point light sources every frame. It might still work. Why? Because there just aren't that many surfaces, right? And most of the problem that we have right now is the fact that we do depth peeling. That makes the cost of a render 4 times more than it should be. There would be no depth peeling in producing the lighting. Because remember, we're not trying to get pixel accurate transparency or anything like that. We're just trying to get an approximation for the lighting. Furthermore, the cube map doesn't have to be particularly high res. The cube map could be 64 by 64, 128 by 128, a drastically smaller size than what we would be using to render the actual game. And so really the only problem that we would have is the fact that we've got sprites in the world and we would have to sample from their textures in order to correctly produce the occlusion necessary for the fact that things are silhouetted. We could even use that if we had Texture Atlas. So we may have to go to a Texture Atlas to do that, if that makes sense. Because in order to get the speed up for something like that, we can't be switching textures every quad like we are right now. We know that that probably has to go, and that would definitely have to go once we're doing even more passes than we are right now because of things like the lighting. But this is a pretty reasonable scheme, right? I could convince myself that this would produce a fairly reasonable result, and I don't know. It seems like something we could try. Basically, the algorithm is pretty straightforward, right? It's just scatter point lights throughout the world based on wherever we think they need to be. For the current simulation step, gather up all the light sources in the region. Let's say that's 100. Multiply that number by like at least 10 by just shooting 10 random rays out from each light source and seeing what they hit and sticking a light source there and then rendering those into cube maps. That's the entirety of the scheme, right? And so we could take that set of lights, we could, again, push it through as points that render into these cube maps, and then we would just sample our lighting from the cube map. That'd be it. Would that work? I have no idea. It's purely me just randomly guessing about something that could work. I have no idea whether it's would be efficient or not. It could be, it might not be. We also could consider ways that are more reverse than that. People actually do sort of like weak radiosity, or I shouldn't say radiosity, weak sort of ray tracing on the GPU as well. And we could do something like that. One of the advantages that we certainly have, we don't have very many primitives. So doing something like voxel cone tracing on our scene would not be very difficult, probably, I'm guessing, because there just isn't a lot there. So I don't know. So it's possible that maybe is a more sensible way to do something like that, because that's something that operates entirely on the GPU and doesn't actually require any CPU participation whatsoever. However, like I said, I don't know, the accuracy of something like voxel cone tracing can be kind of iffy because voxels are very expensive. 3-dimensional things eat up memory very quickly and eat up processing power very quickly, much more so than 2D things. And so you do end up in a situation where something like voxel cone tracing can be pretty tough to get working in any reasonable sense, specifically because of that nasty cubed element of everything that you do. So, again, something like that might be more sensible because, again, we do have a very low primitive count because we're a sprite game. So it keeps the number of things we're doing much more bounded. And presumably, we would have more flexibility there to do something like voxelize things or whatever else we might want to do to them is not going to be as costly. But I don't know. Um, it's a tough call because I don't really want to, like I said, I don't want to spend a huge amount of time going down the path of like doing lighting. I just want to do a scheme and then say that's the lighting, and we'll just, it might have some drawbacks, but we'll use it. And so I don't know which scheme is the one that's going to be the most likely to succeed reasonably. And normally the course of action that you take when you're working on a render is you try a bunch of things, and you pick the one that seems to work the best. That's not really an option for us here, so we kind of have to make a good guess ahead of time. Well, I guess one thing that I could say is that there certainly is some attractiveness to using a system that doesn't involve the CPU, or rather doesn't involve the bifurcation of the renderer into two parts. One part that does the light propagation, like ray tracing in this case, and another part that does the actual rendering, which in this case would be on the GPU. So a scheme where we rasterize the light and then use some kind of sampling from that rasterization, like something that is voxel cone tracing-esque, certainly seems attractive, right? Like, because that allows it to be compartmentalized in the renderer, which also allows people who want to do a port of Handmade Hero that is to a platform that can't afford to do anything particularly nuts. They could basically cut out a lot of that stuff in the port. So, I feel like there is some architectural niceness to saying the renderer does the lighting, and it does it however it wants, right? So it's hard for me to say, but that does seem kind of attractive. So sort of a lighting scheme that just sort of did something on the GPU that rasterized the light into some kind of a lookup system, and then from there produced, whatever the whatever the approximate lighting version is. But yeah, it's tough. I can't really think of what the right way to progress is. I know that, for example, on like Little Big Planet, they did something like that. Alex Evans, I believe, is the fellow's name, who did the render for that. And they did something that was kind of a scheme on the PS3 that did lighting in sort of a rasterized format that was not full voxel cone tracing, but that sort of did a similar situation. I don't remember. This is not what I wanted. Can I go to scholar.google.com? Is there a more for that? No. It's probably no one's written a paper on it. Yeah. Well, let's put it this way. There is a lecture out there by Alex Evans on, maybe I could just do Alex Evans renderer lecture. Maybe that would work. So this might be what we want, although, is that the same Alex Evans? I guess what I would say is I feel like we kind of want to have some idea of what we're going into first. Yeah, okay, so it is. This is a pretty great slide. I love that. So this is, this is the thing that I was talking about, that I was thinking about for Little Big Planet. Because, like I said, you know, we have sort of a similar situation to Little Big Planet in a lot of ways. We don't have really long view distances, for example. We're just talking about a couple slices of a level is all we ever look at, and it's pretty clearly bounded. And so you can see here, like they're talking about sort of the voxel cone tracing kind of approach. They have volume textures that they store the lights in. I talked about this a long time ago on Handmade Hero. And so they kind of go through like, okay, so they talk about irradiance slices, and they basically say like, okay, these are some, I like how these are like drawn with like magic marker or something. I like that a lot. So basically what they do is they take a light source and they slice the world into slices based on the light source, and you know that's basically going to make a voxel, right? It's going to make a 3D thing of information about the light, and you can see that like what they do is they say, well, all right, I want to basically store lighting information into these slices so that I can accelerate rendering and not have to actually trace lights around. Now, how they do the actual tracing, I'm not sure. Let me see here. So here you go. Render a front and back Z buffer for each slice. So that's basically taking the range like of to figure out what's in that slice, right? As far as geometry is concerned. and minimax Z. So tracing the site is just a matter of comparing lots of Z's. Okay, I see. So they're basically just saying like, okay, we're trying to ray trace in a slice. We can write directly to volume textures, so we can probably avoid some of the hassle here. Find the nearest point in the slice volume and sample will become more efficient because we're orthogonal. So that all makes good sense, except, yeah, like they were saying there, that's for one light, which isn't really going to help us. So I'm kind of interested to know. Here's a surface function. So this is more like what we want, right? We are sort of 2.5D. And this is sort of talking similar to what we were talking about, where we're saying like, yeah, you know, we could do cube maps in here or something like this based on a grid, and then we'd sample from those or who knows what. So this is their technique, which is different from this. We're going to compute on the fly as a GPU at low resolution based on potentially large number of light emitters. Yes, that's exactly what we want to do. Computing it in screen space also seems reasonable. Let's see here. Additively composite each visual light by intersecting its oriented bounding back to the slice of the volume. Okay. That's pretty easy to do. They're just saying like blob in the light sources to the volume that we're tracking. Depends on direction of the irradiance at a given point is often representative used for our harmonics. Okay, so we could get into something like that. It looks like they did something even simpler, which is not even spherical harmonics. They just have a basic, like a basic idea of the light contribution. Let's see here. This is just figuring out how they're actually using the gradient, but that's a little bit more specific. So that's pretty cool, right? Like, and we don't care too much about shadows, right? Like, again, occluders is sort of something we'll have to think about a little bit, but yeah, I mean, that's the kind of thing that I'm just thinking, like, I don't know, if we went down a road that looked more like that, it seems like maybe that's a smarter thing to do, because we do know we can kind of slice the world up relatively predictably, and it's fairly confined. So producing the lighting in that sense, if we did something that was more about sphere and volume, and I think I talked about this when we originally talked about lighting way back when on Handmade Hero, talking about propagating light around in the grid. I just wonder if that might be sort of a more feasible way to do it than to try to do something fancier. And I don't know. It's really hard to say. You now know basically all I know about like what we maybe should or shouldn't be doing. And so I don't know if we should just flip a coin about what we end up trying. It's a good question. And like everything else, right, it's annoying because the only way to know which is the right solution is to try everything and see what ends up being the most cost effective for, getting good results and not being too, compute intensive. So I don't know. I really don't. I don't have a good plan. It feels like one of those flip a coin kind of situations, and I don't know if there's any way we can really narrow it down any further. I like the idea of treating lights as a volume, and I like the idea of voxelizing things. I just don't know how well it works out in practice. One of the things is if we were to take, let's say, a fairly high-res sample of the world. So let's say we took a 1024 by 512 or something sample of the world, right? And I don't know how much information we'll need in order to store some useful lighting information in that. But that's a very high-res version. So let's say it was, we're still talking about, maybe 4 bytes per sample there. So that's going to be, let's see, that's going to be what, 2 megabytes? Per slice of a thing. And so if we wanted to do a certain number of slices through the world, even at such a high resolution, what would be the, cost for that kind of thing? Well, we could afford quite a few slices at that point. Like, let's say you wanted to spend 256 megabytes on lighting, which is not a huge amount. We could do it. That would give us 128 slices through the world, which is a lot of slices, right? So it seems to me like the voxelizing techniques, just back of the envelope, the problem would only be if the computation was too expensive in them, because it really doesn't seem like the memory is going to be a problem for what we're doing. Right? It seems like the memory for what we're doing would be fine. So, it might be that something. Let's just take a look here. Let me see what we would have for if we were to do something like voxel cone tracing. Oh, my goodness! This is not a very fast server, is it? So we're on a pretty fast connection here. This is a 1 gigabit connection here, but that is, I guess it's from France. Maybe it's got to travel all the way around the world, right? So if we were to do something more like this, where we actually kind of, went nuts, this kind of technique is kind of amusing, right? So the idea here is that, if you are to produce something that's seems kind of expensive voxel-wise, right? So let's say that we produced something of our world that was like 1024 by 512 by 128 or something, right? The idea is, well, once you produce something like that, you can then pretty cheaply filter it down, right, to some bitmap versions. So you can then do, when you have your 1024 by 512 by 128 one, you can then do your 512 by 256, right, by 64 one, and your 256 by 128 by 32, and your 128 by 64 by 16, right? And it contracts down each time. And so what you do when you talk about sampling the lighting for something like this is you can kind of sample everything that's out in a direction light-wise by just sampling from successively lower res versions of the voxel. Because tracing through the voxel would be way too expensive per pixel, but we could take only a few samples, one really close to us, one further away, one further away from that, that are from higher and higher coarseness, or I should say lower and lower resolution, to do something reasonable like that, right? And you can kind of see like they get good results from things like this. It's a bit finicky of a process, but yeah. So you can see this is the part that I wanted to look at. So if you want to do indirect illumination here, what's interesting is I really don't know. I haven't read this paper and implemented it or anything. So I'm curious to know what they do for indirect light. I guess what it says here, to compute indirect illumination of a point light is more involved than we use a two-step approach. First, we capture the incoming radiance from a light source in the leaves of our steam representation, storing incoming radiance not outgoing will allow us to simulate glossy surfaces. We filter and distribute the incoming radiance over all levels of our octree. Finally, we perform approximate cone tracing to simulate the light transport. Writing the incoming radiance in the octree structure is complex, therefore we will from the moment assume it's already present in the octree structure before detailing the process. All right, so where is that? Here we go. In order to simplify the explanation, let's consider that our octree is complete so that we can then launch one thread per leaf node. Okay, we'll perform 6 passes, blah, blah, blah. Distribution over levels. At this point, we have coherent information. A simple solution would be to launch one thread for each voxel. The higher level fetch data from the lower level, nonetheless. The advantage for shared voxels, blah, blah, blah. So I'm not sure without reading this in more detail, I really know exactly what they're doing here, but it sounds like what they end up doing is the volume transfer. Well, you can kind of see the diagram here, actually. The volume transfer is kind of just like a propagation through the octree. So you kind of like take surfaces and you splat. It is basically photon tracing, right? In fact, here it said after photon splatting. You just kind of like propagate a little bit out to give you some amount of bleed, and off you go, right? And I assume they do this in a somewhat multi-resolution fashion, but I don't know. So you can see here what they do is they take the light position and they basically treat the light as, they render the world from the light source and treat that as basically like a where to sort of shine, where to sort of seed the lights into the voxel, right? So I feel like we will want an approach that's simpler than that, just because I feel like that's going to really be fairly demanding. That's going to require atomics even. So yeah, it's really tough to say. So I want to get a decision by the time we end the stream today because, you know, walking through this process, and again, the reason I include this on the stream is just because this is what actually happens when you're doing game development, right? You have to make decisions like this. Like I said, the decision here probably would be we want to try a couple different things, and I don't really want to do that, but just thinking it through, despite the fact that it seems like there's more information in the area of sort of the spreading, splatting, Little Big Planet, Fox cone tracing kind of thing, I feel like I actually like the point light propagation model a little bit better. And the reason that I like that model a little bit better is it just feels more coherent to me. Like, the voxel thing feels a little too imprecise, and I feel like I would constantly be wrestling with the discretization of that voxel and what gets stored in a particular node in like ways that are problematic. So it kind of feels like to me doing something where we've got, where we've got those point lights seems a little more sane. And the first step of the voxel cone tracing process is basically that step that I had described before, totally without having looked at the voxel cone tracing, which is that taking the light source and splatting out point lights is actually the first step of their process. That's the photon seeding, right? That they were talking about. So that step has to happen one way or the other. And so to a certain extent, I feel like I might want to start with the idea that that's going to happen regardless. So we're basically going to produce a series of points. And we're just talking about how we're then going to use those points. But at the beginning, we're going to produce a series of point lights, one way or the other, really. It would seem. And so when you produce that series of point lights, it's really a question of what are we going to do with them after that. Rendering cube maps was one option, and then the other option is, well, we do something more like the voxel or the splatting. And that would basically say we take those light sources and we splat them into some kind of a volume texture, and then we sort of let the volume texture do something interesting in terms of propagation. And so my question is it worth that? Does that actually get us something? Or are we just wasting our time and we should have just rendered cube maps everywhere? Or if not cube maps, then something else, right? Should we just render some other thing that captures what those point lights are actually representing? And again, it's kind of hard to say. But I feel like if we can produce those point lights relatively quickly, and who knows, maybe the right answer is to produce those point lights in more the fashion they were talking about. But for example, I'm not really sure how they do something like a skylight at that point, because a skylight, I know exactly how we would do a skylight with our scheme. Are they suggesting that if they were going to do a skylight in the voxel cone tracing world, they would have to render from many different points on the skylight and then seed the light out that way? That seems rough, to say the least. I don't know that that would really work. It seems like that might be cost prohibitive. Whereas ray tracing from different points on the skylight is kind of a more constant time manageable process, right? So let's see. Suppose we were to CPU ray trace light propagation. and generate point lights, right? 2, render cube maps at low res throughout world. And let's say we maybe do something like, 64 of these. 3, render. So looking at those 2 steps, I don't think they're that complicated, right? And I feel like, furthermore, because we keep textures on the CPU side anyway, because we want to support software rendering, and that doesn't seem prohibitively expensive because CPUs always have more memory than GPUs anyway, and we don't use that memory for anything else. So keeping the textures on the CPU side doesn't seem problematic. So when we trace, we will know what color we hit. So CPU ray tracing doesn't seem to be something that would be prohibitive, especially because we don't have that many primitives in the scene. So I feel like the biggest stumbling block here is, what is the acceleration structure? Because right now our world is not really sorted into anything that we can ray trace into particularly coherently. We don't have them sorted by anything particularly convenient. I guess we've got world chunks, and we could keep the world chunks relatively small, and maybe that is sufficient. But I don't remember what the actual size of those world chunks are. So maybe that's good enough. Maybe the world chunks would be sufficient to keep the computation cost down. But that would really be the question there, would just be, how expensive would that be, right? Producing the point lights from that process then is pretty straightforward. Whenever we have a hit, we just sample the texture, and we produce the point light color based on its reflectance, right? Based on its color. So that seems pretty straightforward. Rendering the cube maps at that point is real easy. You just take the array of point lights and the current scene geometry, and you render it with a Z buffer, and you let it occlude. That's about it. Right? I don't think there's much more to it than that. And that would produce the cube maps. So the real question is just, is there enough GPU power to render, these cube maps? And I guess, like I said, we would definitely have to have a texture atlas or something. It's not going to fly with the number of texture changes that are in there now, but that's not, an impossible thing to do. We could just use a texture array and be done with it. So I don't know, that seems like what I would probably say is the best approach to getting some reasonable lighting without too much. This is the only thing that scares me a little bit about it, is I don't want the game to have to do a lot of work maintaining a separate acceleration structure in order to do the ray trace acceleration. But it might be that since we've got the world chunked up already, that's sufficient because there just isn't that much stuff in it. But I don't know. So I'm going to go ahead and go to the Q&A. You've heard my thoughts on this, kind of my just exploration of it. And so if you've got opinions on it, or questions about it, now would be a good time to air them, because tomorrow I will probably start coding something. So if you have a notable objection or idea that needs considering, now is the time to get it in there before the typing begins. MTS Mox says, don't we already need acceleration because the lookups for the closest traversable is already slow? Yes, but unfortunately, and this is the eternal bummer, right? Is that the acceleration is a different kind, right? And so maybe, this is why I was saying, like, maybe it turns out that they can be the same, because if the world chunks just work for both of these or something, then maybe it's fine. But the problem is that one is a closest point query. Kind of a thing. And one is a line query. Right? So in the case of wanting to accelerate the closest traversables, which we definitely want to do, what we're looking at doing there is saying, well, okay, we've got the world chunked up in some way. A straight up voxelization of the world that just deals with chunks will just work. Because we know we just want to search for whatever is in the closest area, right? So we know this will work for that just fine, and that's all we want to do. And we already sort of have that, so all we have to do is just actually start to preserve it in the sim region. When we bring things into the sim region, we want to keep that. But for line queries, it's a little bit different because line queries want to do this sort of thing, and they need to be able to figure out what's the thing they will first hit. And so the problem with that is that if you have a voxelization and the first thing you're going to hit is way on the other side of it, you're traversing like tons of voxels to get to the answer, and it ends up not being particularly it ends up not being a particularly fast solution, right? And so the question is just, will that kind of solution be fast enough? And if it is, then great, because like you say, we know that we will be taking advantage of some acceleration structure, probably something based on the world chunks, because we're already packing and unpacking things from them, so we'll probably just keep things. We pull them in the sim region, we'll keep them arranged in a spatially coherent way. But the question is just, does that produce a fast enough line query? And I don't know. But even if it doesn't produce a fast enough line query, we may still be saved by the fact that perhaps we can put something on top of it that does, so that we don't need two acceleration structures. We just augment our existing acceleration structure with one more thing. For example, we might put a secondary layer on top of our grid, our world grid, that's a little more like an octree. So for nodes, for times when there's just empty space there, we'll record the bigger empty spaceness of it so that the ray tracer can skip through it. What are these called? They have a name. Oh, crap. Can't remember the name. So there's a name for this process where you basically have a world grid, let's say, like we will have. And I need to draw a fairly dense one here to get the point across. Right? So we got the world. Oh, you know what? Now I think about it, this works in 2D too. So there, I can make a simpler diagram for you. I forgot this is not something that requires the full volume to understand how it works. So the idea here is, well, okay, I'm going to ray trace through a grid. The slowness of ray tracing through a grid comes when you don't hit something. So if I start my ray trace here and I start tracing through the grid, if this cell contains the thing I hit, right, that's great because I'm going to get the answer right away. The problem comes when there's nothing in that area and I end up having to go all the way out here. Because now I'm looking through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11-ish. I don't know how many there exactly be, something like that. 11 cells for the answer, which is a lot of iteration, right? And so what acceleration structure you can use for this is to store basically empty space specifically. So in every cell that doesn't have something in it, you store a sort of, you don't even have to do it per cell. You can do it as sort of a separate region on top, which is basically just you store cubes, or I should say not cubes, right rectangular prisms. So like rectangular shapes in 2D that are empty. And you test against those as you pass through them. So you go here, you go, oh, I hit this thing. I know I can skip all the way to here and start my ray tracing there, which stops you from having to consider any of these cells because you already know they're all in the empty area. So we might be able to pile something on top that doesn't really conflict, that's just an augmentation of the data structure that would allow us to do the ray tracing faster on it, right? So it's entirely possible that we could do something that just builds on the scheme that we already have so that we don't have two schemes, which starts to get a little long in the tooth, in my opinion. If we have to have one for our closest point queries and one for our ray tracing, that starts to get like, how many acceleration structures are we really going to have here, folks? Right? So that's something. Jurazi says, why not use single distance fields? I assume you mean signed distance fields, but I'm not 100% sure. If single distance field is a thing, I don't know what it is. But if signed distance field is the question, why not just use signed distance fields? They're best for line queries. Sorry, a bit of context, just joined the stream. So yeah, that's a good question. Signed distance fields obviously are pretty popular in like the demo scene, right? And they have kind of the nice process that they're relatively easy to ray trace through because at any time you can figure out roughly how far away you are from the nearest surface, so you know how far you can step along the ray without hitting anything, right? And just for those of you who aren't familiar with these, I'll sort of give you a little bit of a breakdown. Actually, I guess I don't really want to draw it quite that way, so I'll just pretend this is a very dense grid, right? So let's say that I wanted to ray trace, and let's say for sake of argument, because it's the easiest thing to talk about in a signed distance field, let's say I've got some spheres, right? So I've got a sphere that's sitting here, and I've got a sphere that's sitting here, and I've got a sphere that's sitting here, right? And now I want to ray trace, and this is what I'm doing. So I'm looking from here, and I'm looking that direction. So obviously, the thing I'm looking for is the ray trace of that sphere, right? I want that intersection point. Well, if I take a look at this, I could say, all right, if I wanted to produce some kind of a acceleration structure for this, I could produce a signed distance field acceleration structure for it, a grid, and we'll see in a minute that you can actually get rid of the grid entirely. But I could say, for any particular point, I could imagine computing what the distance is to every object in the scene from that point, and storing whatever the one is that's the closest, right? So at this point in the grid, right at these points in the grid, I would say, oh, well, the closest thing in this case is there. So the point in my texel or whatever would be that distance, right? And when I got closer, say, to this one, which is here, it would be that distance, right? So at every point in my texture or my volume or whatever, I would just store the distance to the closest object. Now what would happen is, when I look and say, okay, I want to start ray tracing from here, I would look up into the texel at that location and say, what is the closest thing? Well, the closest thing is like probably that far away, which means I can step that far along the ray, right? And now I can do it again. What's the closest thing here? Well, the closest thing here is there. Okay, I can step that far along the ray. And then eventually I look in the sign distance field and I find the distance is small enough that I no longer want to step any further. I'm like, I basically hit something, right? I'm close enough to an object that I can consider it a hit, right? So that's how sign distance field works. And the nice part about them is if you have surfaces whose distances can be computed relatively efficiently, you don't need an acceleration structure almost at all, right? You can use a very simple binning to just kind of go, what objects do I need to look at? But for example, here, if I just had 3 spheres, rather than ever computing any kind of grid or anything, I can just say, well, whatever point I'm at, just compute the distance to each of the 3 spheres, right? And it's exact now. It doesn't have any kind of discretization or anything. And so at that point, you end up going, well, all right, now I just have an acceleration structure that lets me know which rough objects I need to consider. The reason I'm not a huge fan of sign distance field is that they tend to be kind of special case. Like, it's sort of hard to do polygonal things with sign distance fields in a particularly useful way, because you end up having to do the polygon sorting into some kind of acceleration structure anyway. And at that point, it's unclear why you weren't just ray tracing it, right? And the same person suggested a KD tree afterwards. I guess what I would say is the KD tree is the primary way you accelerate ray tracing. And what I was trying to say before is that's the part I don't like about this idea, is I don't want to have to KD tree my scene just for the light propagation step. It feels like adding a lot of complexity. KD trees are what you use for ray tracing acceleration normally. You don't typically use sign distance fields. Sign distance fields are usually if you have very special purpose kinds of shapes, not polygons. Kim Jorgen said, shouldn't we get the frame rate to reasonable range before adding more complexity? How do we know our budget? But our frame rate's excellent right now, isn't it? What's wrong with our frame rate? This machine is like what, 8 years old now at this point? 7 years old, something like that. If I compile our game in a release configuration, I'm pretty sure the frame rate is totally usable, right? Like, I mean, what's wrong with that frame rate would be my first question. Like, what do you feel like you need to fix? I'm pretty sure we already run at 60 frames a second. We definitely run at 30 even in debug. So I'm not sure what the problem with the frame rate would be. If that makes sense. Are there obvious visual differences in these different lighting methods? Well, I mean, yes and no. So all of them are kind of approximate, and it's hard to know what the differences will be apparent in any particular game without doing it. Especially a sprite-based game like Handmade Hero is pretty different from the kinds of scenes you typically would see these lighting models tested on. So we're a bit in uncharted territory to a certain extent, because we don't even have 3D geometry. So I'm not really, I mean, the cubes are, but the rest of it isn't. So I really don't know what the visual quality difference would be between them. Valbus, I'm not planning on putting in shadows. I don't tend to like hard shadowy looks. I like the softer kind of just sort of ambient lighting look. So I only care about light occlusion, like we talked about already. But like hard shadows, I don't want. So those will just be baked into the art assets as a little like ambient occlusion kind of ground thing. That's there, but I don't want shadows in the hard shadow sense. So that I'm just not putting into the renderer in any way, if that makes sense. Illumi25, do you know if your broadcasts have inspired improvements in popular game engines out there? I don't know. I guess what I would say is, certainly for something like rendering, the answer is definitely going to be no, because they're doing stuff that's way more complicated and 3D based than what we're doing. But I guess what I would say is I have heard from experienced developers who've seen stuff on the stream, like the dynamic code loading or stuff like that, or the loop lab code editing stuff, for example, is one common one. Occasionally, we will do a technique that they had not thought of or something that they then go and do. I don't know that that's led to any improvements in game engines like Unreal or Unity or something like that. I have no idea. But those are probably going to be few and far between, because this is a very educational stream, and most of the time I would suspect that the things I talk about are things that experienced engine programmers should already know. And so the chance that I'm covering something that they have not already had to do is not high. That would be what I would say. So once in a while we do cover something that's kind of maybe something that is a little bit more special in that sense, but that's the rare case, right? And the sorts of things that we do on the show that might be pretty interesting, like building with a build.bat file very quickly and architecting the game so it's a very hard separation between the platform layer and the game layer, or things like this. A lot of those are things that modern engines can't even do at this point because they're so overweight and massive. They're like these 3 million line monstrosities, and so either they thought of that at the beginning and it works that way, or they didn't and they ain't fixing it now, right? So architectural things we may do on the stream that might be particularly good or better than average, I think there's a pretty limited degree to which that can have an effect on an existing engine, because either they already knew how to do it well and it's done well, or they didn't, and seeing it on this stream ain't gonna help them because they're already so far down a tangled path that it would be very hard to untangle. Valbus. So all of this is still not a physically based rendering renderer. Correct. So we are not trying to do any kind of physically based rendering. Physically based rendering is trying to take into account the actual laws of physical light transport, the way in which photons actually have to behave to conserve energy, Fresnel sorts of stuff, spectrum criteria, all these other sorts of things. We don't have any of that information in our assets anyway. They're just hand-painted cartoon sprites. So physically based rendering makes like almost no sense at all for something like Handmade Hero. So what we want is not physically based rendering, but we do want some of the physics of rendering to come into play to give us a nice look, right? And that is why I care about things like bounce lighting, and I would like those things to be in the game. The reason for that is because they lead to a softer, satisfying look that's more like real light. We don't need to simulate the real physics of light because our art is itself impressionistic and is not meant to look realistic. But we do want the ability to get some of the physical aspects of light because they produce a nice look for the game, and bounce light is one of those things, right? So yeah, it's important to draw a distinction between a completely physics-based renderer, which is one that at every stage has to take into account the real physical behavior of the light, and cherry-picking certain aspects of light that are important to how light feels and looks, but leaving other parts of the physics of light out, right? A proper physically based renderer should take physics into account throughout. We are talking about taking specific aspects of the physics of light and using them, but only those aspects that we actually want. All right. I didn't hear, but so Kim, you didn't post again though. So did you talk about what you were like? What is the frame rate problem that you were talking about? Did you have something particular in mind, or? I just haven't seen a follow-up on that, so I don't know. I was curious. Nothing? Kim Jorgensen says, really slow on my old PC in debug mode. Did you look to see, though, if that had anything to do with the rendering? Right? And if so, is it just the texture changes? Because right now, we spend all our time in the texture changes. If you run on a modern NVIDIA card, which has no cost for texture changes, it's like a very flat profile for rendering, actually. It's pretty good as well. And old PCs, I don't really care about particularly much either, right? It's like, you know, we can set our minimum platform to whatever we want. Yes, but if your question is more, how do we know our budget? The answer is that we don't, and with rendering, you never do, right? So one of the problems with producing renderers in general is you don't know what the cost will be for a scheme. You have no idea. That is why renderers are, what makes them difficult, is there's a lot of trade-offs you can make, and there's a lot of approximations you can make, and there's a lot of schemes you can use, and you don't know ahead of time which one of them is going to be the one that produces the best visual quality for the time budget you can afford. And so that's why you typically have on a game somebody working, at least one person, oftentimes more than one, on rendering for the entire time. Because experimentation is the only way to produce a good quality render on modern hardware, right? There is no way to know ahead of time, here's what we can afford to do for lighting. We have no idea. right? And we don't know what the slow part of that lighting process will be. Maybe it's the ray tracing. Maybe it's the rendering of the cube maps. Maybe it's just the act of doing the changes of the render targets to target different cube maps. And how many things we render doesn't matter. It's how many cube maps we render that matters. And like all that sort of stuff is just really difficult to ever know without trying. You can make guesses, but you can't know. So I'm really talking more about, hey, here's an example of a lighting scheme. Let's try it. If it doesn't work, then we'll back off. Or if it's too slow, we'll back off. But I don't think it will be, because we can always just say, well, you know, if we need to, we just have a switch that turns off lighting effectively. And if you're running on a really crappy machine, you turn it off. If you're running on some GeForce Titan machine, you turn it on, right? So it's a PC. There's a wide spectrum. There's no chance that what we do for lighting will be so slow that a high-end PC can't do it, because high-end PCs are orders of magnitude faster than the thing I'm using right now. All right. All right, thank you everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org, and it comes with a source code so you can play around with it yourself. We also have a forum site you can go to if you want to ask questions. We have a Patreon page you can go to if you want to support our video series. A schedule bot that tells you when we're going to be live if you want to catch us live, and an episode guide where you can catch up on old versions of the series if you had a topic you wanted to go catch up on. It's really easy to do now. They've done a great job putting in search in there now, so you can actually go search for different topics you want. It's pretty awesome. That's about it for today. I'll be back here tomorrow, same time, same place, for starting to play around with that lighting stuff. We'll see what we would have to do. Maybe try to figure out how to get that ray tracing working to produce our initial seed set of point light sources. That seems like probably the best thing to do. Until then, have fun programming, and I'll see you on the internet. Take it easy, everybody.